Good. Ladies and gentlemen, welcome. I first want to start with setting the expectations right. If you've been here witnessing the previous two speakers talking about automation, etc., I'm going to have to step it down a bit. I'm not going to talk about automating our processes. I'm going to talk about what's in front of that, what you have to do first in collecting the data. The plus side of that, what you get in return, is something really tangible. I hope to make you understand what we do and how we use data at ZF Windpower. But before I do that, I would like to get to know the audience a bit better. I have one question for you. Please raise your hand if you feel that before you can turn data into business value, you have to start by collecting data first and then think about the use case. If you agree to that statement, please raise your hand. Okay, some people agree, good. Who thinks it's the opposite, that you have to have a good use case in mind and then start thinking about what the data, okay, also some people there. And I see some people raising their hand twice, that's the third topic, huh? Who thinks it depends? Yeah, I'm gonna talk you through some examples at ZF Windpower where we did the data collection first. Yeah, but that doesn't mean, I'll come back to the end, that that's the only way forward, of course. Okay, let me first introduce ZF Windpower. Who has ever wondered what's inside the white box on a wind turbine you see near highways and on the shore? Well, I can tell you ZF is inside. To be specific, typically three elements are inside a nacelle. By the way, there are wind turbines without a nacelle, direct drives, they have the small egg, but if you see a white box, chances are very likely that there's a ZF gearbox inside. Typically three items: a coupling with the rotor hub, a gearbox, and a generator. And what ZF is doing, we are supplier of the gearbox. And what the gearbox is doing in a turbine is basically converting the slow speed of the rotor into a high-speed output shaft for your generator. But even more important, it's actually a torque converter. So it reduces the high torque from the rotors into a low torque output such that your generator can take it. It is about dealing with high forces. And these high forces, they are crucial in our business. Understanding these high forces and these high torque levels is the essence of why we did what we did in the examples that I'm about to show. The picture I showed in the beginning was a very old turbine. It was a small turbine. Nowadays, turbines have a size like what you see here, or at least the nacelles on the pictures. For Vestas, this is a 15 gigawatt gearbox producing 80 gigawatt hours per year, or around about 20,000 households of energy. Now these things are big. Yeah, it's a typical 40-foot container hanging on the side of this nacelle, standing on a pole 200 meters above the sea level. And what we produce now is not just the gearbox, but it's an integrated powertrain, meaning those three elements that I talked about in the beginning are now combined into one product, and one product is about 220 tons. Yeah? To put that in perspective, around 100 Tesla Model S's. Now, I mentioned torque, big torques, high forces of the rotor blades. Well, this baby can take up to 18,000 kilonewton meters. Yeah? Car enthusiasts like myself, or people that drive an electric car, start to like torque levels when we are about 400 Newton meters. Yeah? Acceleration of a car, electric car, 400 Newton meters, that feels fun. What this thing does, it's 13,000 of the fastest Tesla Model S around. Just to put it into perspective, what it is we are actually talking about, and why simple deviations in our production process can have a critical effect due to the forces and the torque levels it has to endure. Maybe one final slide on who we are. ZF Windpower is the business unit out of the ZF group. but has its headquarters in Lommel, in Belgium, where there's also the R&D center. We have in total 4 production facilities and 1 service facility in the US. Okay, let's get to action. I have 3 examples. The first example is what is called our parameter validation, and it has to do with our gear grinding process. Gear grinding, for those that are not familiar to it, has to do with a grinding wheel that takes off very limited, less than a millimeter material of your gear that you're producing, after heat treatment, that is. And when there is a production issue or an issue in the gear grinding process, you can have a black mark. Is it visible? Yeah, it's visible. A black mark on your tooth profile, which is called grinding burn, which actually changes the material properties of your steel, making the steel more brittle, and therefore it cannot handle these high loads anymore. Yeah, so this is a very important thing. We had a big issue on this, and to understand the gear grinding process a bit better, it's the operator that has this knowledge and expertise. So I'm not talking about a fully automated process here. It's really the operator that has to make judgments based on measurements he does for every single part and adjust his process accordingly. We did a Six Sigma project, and it turned out that what the operator filled in as parameters to steer his process was actually quite crucial for understanding, or could lead to this grinding burn effect. In this example, for instance, he changed one parameter, the R725, put the same value for the next parameter, and we had this could lead to a scrap issue. What we build here is, by connecting the machines, we were able to check the parameters the operator was putting into his machine with some threshold values from the process engineer. Yeah, so the expert, he was setting up boundary conditions for what is a good setting for each of these parameters. And by talking to the machine back and forth, we could actually interact with the operator prior to him starting the machine. So the value was sent to a server, it was checked, and some communication came back. If it was within the tolerances set by the process engineering, green light, operator can go. If it was not within this tolerance, there was this feedback, and the operator still has a chance to say, yes, I know, but this is required to make a good part out of my gear. But at least then we had stored this communication to the operator. Yeah. So if all was green and it was still scrap, we knew that it was not the operator making a mistake. There's something in the process that we didn't have under control. If, however, the feedback was, this is out of tolerance, are you sure? And the operator still says, yes, I'm sure. We know that we have to train the operator. Yeah, maybe with interacting with him a bit more on the machine. But that is what we did, what we built. We built it together with Bright Eye. Lovely people, they have a booth here. Go and visit them. But that's all of advertisement I will do here. But it had a dramatic impact on our cost of scrap. This is one example, but it was clearly black and white. The day we started with introducing this technology, by using the data from our processes and what the operator was doing with it, we were very much able to reduce our scrap cost. And by reducing the scrap cost, we were also able to reduce the indirect quality cost of the quality reporting, the root cause investigation, etc. And essentially also the tasks here in orange, which are processes that are required to check for grinding burn, but our customer wants to hold on to this check. So otherwise these would also be green, but it's in relation to our customer that we kept doing that. In my second example, I'm going to talk about our closed loop heat treatment process, where before the gear grinding, there is a heat treatment process. Made some sketches in PowerPoint to take you through what is actually happening. So what you see here is a magnification of a gear, of a gear profile as good as I could draw it into PowerPoint. And the red line is the profile of the gear when you do milling and hobbing, so before the heat treatment process. The heat treatment process itself is by putting the part into an oven under a carbon atmosphere for days on end at 950 degrees. And what happens basically, when you see the green line moving, that is carbon atoms going inside your steel, creating a hardened surface which you need for your teeth to be able to withstand the high forces. Yeah. The thing here, yeah. After the heat treatment comes the grinding process, which I already described. That is removing material. But like I said, it's the heat treatment process is not a stable or perfectly predictable process. It's not linear in any way. You have distortions of your part, and the operator on the gear grinding machine has to correct for the distortions in your heat treatment process. So that means it's not always the same amount of material that he's removing from the surface. Yeah? The difference between the red line and the blue line is not a constant. But that means that there is a remaining hardness depth which is crucial for the performance of the gear. And that is specified by this yellow line. So we have to make sure that the blue line always is away from the yellow line, but more importantly, that the green line is always further away, further in the material than the yellow line is on this depiction. Like I said in the beginning, we have a lot of data. We have a lot of data from the entire process chain of the different process steps into our gear grinding. We all store it into our data warehouse, and what we did in this project is to set some intelligence on the data which we can use to feed back into our process chain, be it for the milling or the hobbing, but I'll not take you in that aspect, but specifically for this talk today into the heat treatment process. The heat treatment process is shown here. You saw this graph maybe on one of the earlier slides. I didn't explain it. What needs to be understood is that the heat treatment process itself also is not linear, meaning it takes a lot longer to add a few millimeters or a few tenths of a millimeters of hardness depth at the end versus the beginning. So the yellow box here is an indication that for 1/2 millimeter extra, it takes 3 hours extra to do, while in the beginning, in 3 hours, you have more than a millimeter of hardness or carbons in your surface. So it is really important. The longer you want to make your heat treatment process, the deeper the green line will go into your material, but it takes you exponentially longer to actually achieve those deeper values. The worst case, however, is when your hardness depth is not enough. Yeah? Then, due to these high forces, your teeth cannot withstand the forces. They will start to crack. A small metal particle will let go, and this simply creates an avalanche of metal particles, cracks, and so forth in your gearbox, leading to a catastrophic failure on the picture on the low end side. So this is the absolute must-avoid scenario. And what we do, because you cannot measure the hardness depth, well, you can, but then you have to saw your part in two, and you can actually look at the part. You see a discoloration in your metal, and then you know how deep the hardness depth was. But obviously, you don't want to do that with every gear you produce, because you don't produce a gear anymore. You destroy it. So what we had to do is we had to specify our heat treatment process to deal with variation. So the curves, there is variation in the process. And we had to stay at the higher end of the scale, just to, if the operator had a highly distorted part, had to remove a lot of material, the hardness depth was still okay. That's basically what we did before we had this process. But with combining the data from our heat treatment process in the green cylinder, from the grinding process, the purple one, and also the yellow one, all the other processes involved in the chain, we were actually able to calculate for every part what is the remaining hardness depth. And not only calculate, we can also visualize it for our process engineers to tune the heat treatment process, and also for our quality inspector, we could have an educated guess of what the hardness depth was for every part. So the quality inspector now simply didn't have to rely on, well, we've put in enough extra heat treatments, so it should be okay. Now he has a number from which he can confirm that it is okay. But the saving in this is not that. The saving is in the reduction of the heat treatment time. Yeah, so by knowing, oh, but actually, when we look at our data, we always have this excess of hardness depth. We were able to reduce the furnace time. Furnace time is gas cost, the cost of burning the gas, but especially also important now, CO2 reductions by not having to burn gas endlessly. Stepping into my last example, it's what we call our selective assembly. So this is what happens when we put it all together in this powertrain or in this gearbox. And specifically, one element of that, which is the planet carrier. We have multiple stages in our gearbox, multiple steps in reducing the torque. This happens with a planet carrier, which runs in a ring gear. And such a planet carrier is built up of gears, bearings, shafts, and then a cast iron planet carrier, like you see on the picture here. And what the assembly operator does, he simply has to put them together. Yeah, put a gear inside the planet carrier, put a bearing in, and put a shaft, and that a number of times, depending on how many gears there are, ends up with a product like what is on the picture here. But what is crucial, and I want to give this reference, this is highly exaggerated. Yeah, reality is not like this. We're talking about tens of millimeters or even less, but like said in the beginning, because the impact can be so high, based on the tolerance chain for each of these components we have, it is possible that we end up with what is called a center shift, meaning that the gear is not dead on in the center where it actually should be. And it's this center shift that we want to get under control, because if, for instance, one gear is sticking out further in this planet carrier, this becomes your weakest link. This is the part that has an even higher load on it than what it was designed for. So this one is the one most susceptible to breaking and causing these catastrophic failures. Of course, the opposite is also true. If the center shift is in the other direction, a part can be underloaded. It doesn't contribute that well to the team effort. Now, before we had this project, the assembly operator simply was able to take the gears and shafts as it was most convenient to him. Typically, start with the first gear on the first pallet, the first shaft which was closest to him, and he could just assemble it the way he saw fit. But by combining the data, the dimensional data of all these components, we were able to calculate which is the best combination the assembly operator had to make in order to create a more even load distribution of all the gears in the team. Yeah? By doing so, there was no weakest link anymore. Everybody in the team contributes in the same way, which makes your team the strongest. Yeah, and just to give you an example, it's then no longer planet gear 1 combined with planet shaft number 1. It could be planet shaft number 1 combined with gear number 4, or planet gear number 7 combined with planet shaft number 2. Now, how we dealt with this variance introduced by the operator on the left-hand side of the picture was again by introducing safety factors. We designed our gearboxes to handle a certain torque value, and we then subtracted 10% of that, just to be on the safe side, because there is always statistics possible that there is a weakest link. So we always had to assume the worst case scenario, And actually, we told our customers, please don't, or no, we didn't tell it that way, but we made sure that we gave them a product which in theory could handle more, but we couldn't sell it as such. By doing this, we were able to let go of the safety factor. So the monetization in this is in having fewer design iterations. Yeah. So the safety factor can be removed. We can sell the same product to a customer that wants a 10% higher torque value, and we don't have to do anything, basically. People tell this, oh, this is then for free. Yes, it's for free because it's using the data that we already had, but of course, setting up a system like that is not for free. And what did we do? Just to give you some insights. This is quite a complex story here. It starts with our own dimensional data from our in-house produced parts, like the shafts and the gears. But the bearings, for instance, we don't produce, we source them. So we also had to find a way to automatically get dimensional data from our suppliers, because we need that information. We had to build a configuration tool such that we could use this for any gearbox we have. And then we had to tackle the communication with the operator. In the initial scenario, operator could do whatever he wanted. Basically within the work instruction, of course, but he could select the components as he saw fit. We had to tap into the MES system, the shop floor system, such that the operator there starts by telling what components do I have, what serial numbers do I have here in front of me, with which I will be producing this planet carrier. By scanning matrix code, so we also had to apply easily scanning code on the gear. By scanning the gear, by scanning the planet shaft, we told the system which components it had to use in the calculation for the optimal load distribution. So by having that information, feeding that into our analytics cloud, a lot of iterations happened. The Monte Carlo simulation, if you want to know, to get to the optimal combination, and this is then fed back to the operator in our CAA system, or operator guidance system, such that the assembly operator now had to just follow the instruction, and we would end up with a planet carrier with a more even load distribution. Yeah. Last picture I have is just what it looks like now in comparison to the picture in the beginning. All right. Ending here, these were my 3 examples, but let me take you through my key messages, or what did we learn from that. Coming back to the beginning, the chicken or the egg story, do you need the data first or do you need a good use case? Well, it's a tough one, but I hope to have shown you that you can start by collecting data. A good use case is indeed crucial. You have to know why. People want to know the why, but the whole thing only starts when you have good quality data to work with. The second important message that I want to bring is, yes, you need process knowledge. You need process expertise. You need people that know what the data actually means and how you can optimize their world with the data they have. But data is a job. Not everybody is able to deal with data. Not everybody is able to understand how data is to be collected, how data is to be stored in a structural way, how you write a Python code to do an analysis, etc. So you need a multidisciplinary team if you want to tackle a data use case in your shop floor or in your processes. And then the last one, most important, start small. Yeah? Try to bring value as soon as you can, because the quality of your data relies on that. If people don't have a data mindset, you will have poor data to work with, meaning the outcome of your algorithm will be bad. Shit in is shit out. Yeah? So make sure that people know and understand and feel, oh yeah, I know why I have to keep my data good, and I know why I have to log this information, because it brings me this in return. If you take too long before the people that provide you with the data or with the insights If it takes too long, they get lost. You get lost, and your use case is gone. Yeah? So that doesn't solve the chicken and the egg, unfortunately. It's a bit of both, but I hope to have shown you what you can achieve by tackling a bit of both at the same time. I don't know whether we have time for questions. Okay. Anyway, I'll be here. I'm not running away. We have a lunch break now, so maybe we can meet and see each other there.